This is John Black, super chemist. We're here today to talk about what Faraday's constant is. Right here it says electric charge per mole of electrons, and it's 96,485 coulombs per mole. Well, what does that mean? That just means that how much charge is in if I had a mole of electrons here in my hand, how much charge would I have? This is how much charge you'd have. That many coulombs. We'll go into coulombs and what they are later on here. But let's say you're doing electrolysis and it takes one electron to reduce one molecule into your product. Okay? If it takes one electron to do that, then that means it takes 1 mole of electrons to reduce 1 mole of reagent, right? Because if you have a 1 per 1 on the mole and the electron, you have the same amount. If you have a dozen electrons, then it'll reduce a dozen molecules. If you have a mole of electrons, it'll reduce a mole of electrons, right? A mole of molecules. Now, how much energy does it take to reduce a mole a mole of molecules? Well, that's what Faraday's saying. He's saying it takes 96,485 coulombs. Now, it's a given what a charge is on one electron. One electron is 1.602 times 10 to the negative power coulombs. So if this is your charge right here on one electron, what's the charge on a mole full of electrons? I would just multiply this charge times a mole. Just like if I said, if there's this much charge on one electron, and I said there's a duet of electrons, you'd be like, what's a duet? I'd say 2. You'd say, oh, well, I times that by 2. If you had a dozen electrons, and I said this is the charge on one electron, how many is on a dozen electrons? You'd be like, what's a dozen? I'd say 12. You times it by 12. It's the same thing here with a mole. It's just a mole is just a number. Just like Google is 10 to the 10th, Googleplex is 10 to the 100th, a dozen is 12, a score is 20, a mole is this. So that's how Faraday gets his number, his Faraday constant. You might say, well, what good does that do me? Well, if you're doing electrolysis, it'll help you figure some stuff out. First, let's go into what is a coulomb, okay? And most people know what an amp is, so let's go over what an amp is first. An amp is a coulomb of energy that passes a specific point in a circuit in 1 second. So, if you have a circuit, like right here, here's your battery or your power source, and here's your light or your whatever sucking up using the energy, right? Now look how I have this little mark here. That means 1 amp, if I have 1 amp going through this circuit, that means every second I have a coulomb of energy passing this point right here. Okay? It can be anywhere in the circuit, as long as it can be here, it can be wherever, but you have to keep that specific point while you're counting your electrons. You can't move it around the circuit. Now, how many electrons are in a coulomb? Well, we know this ratio. It's a given. 1 electron has this much charge or that much coulombs. So we can write this ratio either that way or that way. I choose to write it this way. When I do the math and I divide that, I get this number of electrons per coulomb. So that's how many electrons are in 1 coulomb, or in 1 amp every second. This is how many electrons there are. So what is a amp? It's just a coulomb. A coulomb and an amp are the same exact thing. There's only one difference. An amp is taking seconds into account, right? Coulombs is the amount of energy or the amount of charge you have, right? And I could have that charge sitting in my hand, say, because I have enough electrons to be 1 coulomb, right, in my hand. But if that coulomb isn't moving or going anywhere, then it's just a coulomb. If you start pushing it through a circuit like this, then you count every second. Every second, you count how many coulombs went through, and that's what your amps are. So, what good does all this do? How does it help us? Well, let's do a problem here. Let's say we're given a 3 amp bridge rectifier transformer to get 3 amps of DC power out, right? And we do electrolysis for 10 hours. Now keep in mind, it takes 1 electron to reduce 1 molecule into your product. Sometimes it takes 2 electrons, sometimes it takes 4 electrons. We're going to say 1, so it's nice, easy math, right? So first I want to turn this 10 hours into seconds, okay? And here's how you do it. You take your 10 times 60 minutes per hour, and then take that times 60 seconds per minute, and you get 36,000 seconds, okay? Because to do any of this math, you need seconds, okay? Now, we need to know how many coulombs. We have the time, seconds, 36,000 seconds. Now we need to know the energy, or the charge, that we're going to be sending. A coulomb is an amp second, remember? So a coulomb equals 3, and we are given 3 amps, so 3 amps, and we're given our seconds, 36,000 seconds. We just multiply them two things, and we get 108,000 amp seconds. And as we just said, a coulomb equals an amp second. So we can just change this amp second into a coulomb because they're equal. You have 108,000 amp seconds, you have 108,000 coulombs. Now here's where Faraday's constant comes in. You can take and divide Faraday's constant into the coulombs. We just figured out how many coulombs we're going to use if we use 3 amps for 10 hours, right? We're going to use 108,000 coulombs. Once you divide that, the coulombs cancel out and you end up with 1.2 moles. So that tells me if I had 3 amps and I do electrolysis for 10 hours, and that's for 1 mole, 1 electron reduces 1 molecule into your product. It's not a multiple electron reduction, just 1 electron. You can do 1.2 moles. Okay, that's the ideal. You know how ideal conditions never exist. You're going to have side reactions and stuff like that. But if everything went perfect, which it doesn't, you would be able to reduce 1.2 moles. Now, if it took 2 electrons to reduce 1 molecule into your product instead of 1, like we're figuring out, then you'd have to divide this by 2, right? Because you would need twice as much energy, you know what I mean? And so you divide this by 2. If it was a 3 electron transfer to, reduce 1 molecule, then you would divide this by 3. What if usually the chemist knows what he wants to make, right? Let's say you want to make a mole. This is telling you how much you'll make if you use a certain amperage and a certain time frame, right? Well, that isn't the way a chemist works. Chemist knows he already knows this, what he wants to know, and he knows his amps, right? Because you're kind of stuck with amps on what machine you have, what DC source you have. Your source, whatever it goes up to, and also your electrodes, because if you have more amps, you need bigger electrodes. So your amps are decided by the size of your electrodes and also your source, your DC source. I mean, if your machine only goes up to 3 amps, then you can only go to 3 amps. This is the formula right here. What you want to make, you would plug into there. Let's just use 1 mole as an example to make the math easy, and then we'll do some problems. Let's say we wanted to make 1 mole. We would multiply it by Faraday's constant, and we would get Y. And that's in coulombs, right? Because the moles cancel out and you're left with coulombs. But coulombs and amp seconds are the same exact thing. So your answer Y, you can just transfer over to here and change the units, right? Now you take your amp seconds and you divide it by your amps. That's your amps are, like I said, you don't have much of a choice about what your amps are. In our thing, it was, say, 3 amps, right? So you would divide it by the amps and you would get this number, which tells you how many seconds, because the amps will cancel out You'd be left with how many seconds it took to do this reduction for 1 mole, right? And then you just change it into your seconds into hours to know how many hours it would take to do the electrolysis. Let's do an example. I learn by examples. Me saying this is kind of in 2 examples, and you'll know exactly what I'm saying. Well, here's our first example. Now we know what we want to make, and we know our amps, because our amps are forced on us by the limitation of our equipment. So let's say we want to make a half a mole, 0.5 moles. Plug it into the formula, times that by how many coulombs per mole, cancel the moles out, and you get coulombs. 48,242 coulombs. A coulomb in an amp second is the same exact thing. So in the next equation, you can just transfer this number down here and divide it by your amps, right? In our case, my machine, I have a 3 amp bridge rectifier transformer. So I divide that, the amps cancel out, and I'm left with seconds. This tells you how many seconds it'll take with 3 amps to make a half of mole. Now that's theoretically, you know what I mean? You're not accounting for, you know, loss and side reactions. So you divide by 60, get 268, divide that by 60 to get 4.47. The reason why you're doing this is to make seconds into hours, because 16,000 seconds is meaningless. It comes out to 4.47 hours. So that means it's going to take 4.7 or 4.5 hours almost to do a half of a mole, right? If you wanted a whole mole, it'd take twice as that, you know what I mean? If you had a 2 electron transfer, now this is for a 1 electron transfer, you know, to do 1 molecule. If it took 2 electrons, then you would need twice as much power, which would make this, it would take twice as long, you know what I mean? You'd have to double this. If it was a 3 electron transfer, you'd have to take this by 3, you know, 3 times 4.47. Let's do another example. All right, so let's say you want to make 1 mole. You'd plug in your 1, multiply it by Faraday's constant, you get 96,485 coulombs. Coulombs and amp seconds are the same, so you can just transfer it down to here and divide by your amps. I use 3 amps. Amps cancel out, and you get seconds. You get 32,000 seconds. And then I obviously divide by 60, get 436, divide by another 60, and I get 8.93 hours. So if I want to do a whole mole with 3 amps, it would take almost 9 hours. Now that's if there's no, everything went perfect, which isn't going to happen. So let's say I only had 1 amp. I had 3 up here. It's going to take 3 times as longer because I only have 1/3 the amps. So I took that times 3. For amp, it'll take 26.8 hours to do 1 mole. You can see this plug over here. This is a regular plug that you just plug into your wall. But a lot of electronics, like video games, computers, anything that's electronics, usually has a plug like this where it's kind of a box. You have like a box that you plug in, and the prongs come out of the side, and you plug the whole box in. Those produce DC. That's why they're used for electronics. Electronics uses DC. And a lot of people think you can do electrolysis with these, and you can. You know, if you're doing little and small, you know, like little test tube things, you're not really trying to collect anything. These will not work. These are all less than an amp. They're usually a 1/4 amp, half amp, and you can see 1 amp take a day, and that's if everything went perfect, over a day to do a mole. So what do you think a 1/4 amp is going to take? You know what I mean? It's going to take 4 days, over 4 days. 4 days and, you know, 10 hours, 4.5 days to do a mole. But if you're doing just little time, you know, you just want a gram of something, you know, these might be good, especially if you put them in series to build up the DC, or to build up the voltage, so that way you can build up the amps. But I don't know. They're not really good unless you're just doing test tube stuff. So anyways, that's basically the whole thing about Faraday's constant. I hope I could help somebody. You all have a great day, and always remember, science is great.